Okay, so hello everyone. Um, Good afternoon, and welcome back from the holiday break. Okay, and first thing is that we need to realize that we only have 3 class left, including today's class. We only have 3 lectures left, and so in these 3 lectures, we basically will cover the topics for the incompressible viscous flow for internal flow and external flow. So which is corresponding to the chapter 8 and chapter 9 of your textbook. But the thing is that we won't cover everything in these 2 chapters, so we only cover selected sections. Okay, so the first thing you need to be aware of is that for the chapter 8 and chapter 9, okay, focusing on my lecture notes so that you know that which part is required for the exam, which part is not. Okay, this is the first thing. The second thing, for the final exam, right? The date for the final exam should be on the on the syllabus already, and I will also confirm it. Okay, again, with the department if that date is correct, and I will make an announcement on the blackboard. For the if I confirm the date, but if there are no issues, it should be the date on the written on the syllabus. The form of the final exam will be exactly same with our midterms. The only difference is that we double the time, and final exam will be accumulative, but we're focusing more on the contents after the second midterm. So which is chapter 7, chapter 8, chapter 9. Okay, sorry, not chapter 6, 7, 8, and 9. Okay, so basically 50% of the problems in the final exam will be on these 4 chapters. Chapter 6 is for the incompressible inviscid flow, right? That Bernoulli equation we're talking about. Chapter 7 is that dimensional analysis and similitude, right? Chapter 7 and chapter 8 is what we are going to cover in that in the next 3 lectures. Again, okay, not everything in the chapters 8 and 9 will be on your textbook will be included in the exam. Only half of them. Okay, so focusing on these lecture notes, you know that which part is included, which part is not included. Okay, so this is for the final exam. When I say that the form is exactly the same with the midterm, which means that all the problems will also be the multiple choice problem. I guess that we may have 50 multiple choice problems. Okay, so that because that we double the time, and it also seems policy as before. You are allowed to bring a piece of cheat sheet and a piece of scrap paper, no problem. And we will also deliver on the blackboard the exam, and we are also going to use the same lockdown browser and using the web camera to proctor the exam. Okay, so everything will be same. And I also, similar to our first, so I didn't finish my topic before, right? So I see that 50% will be the contents after the second midterm exam, right? So this also means that so content for the first midterm will take 25% in the final, which is chapter 1 to 3. And the contents for the second midterm, chapter 4 and chapter 5 will take another 25% for the final exam problem. Okay. So this is for the final. And to help you prepare the final exam, similar to the to our first 2 midterms, right? I also create a practice exam for the final. Okay. But okay, I didn't make it available on the blackboard yet, but I will make it available later today. This practice exam for the final exam serves for 2 purposes. The first one, again, okay, to help you to test your, computer, to test your tablet to make sure that you are ready for the exam. And the second thing is that it will provide you some, review, some kind of review for the finals. Okay, and for this review exam, I'm sorry, for this practice exam problems. Okay, all the problems is only cover the contents for the contents after the second midterm exam, which means that all the problems in this practice exam is only for the chapter 6 to 9. Okay, I give you 10 problems there, and because we didn't finish everything. Okay, we didn't finish chapter 8 and chapter 9 yet, and there are 4 problems there. The last 4 problems you won't be able to answer it now. Okay, so it's better that you wait that we finish all the lectures, you can try it. So this is for the practice exam, and okay, and also okay, from our this Wednesday is our last recitation. Okay, so after discuss with TA Yan, okay, and we make a decision that because that the last recitation basically will be a review for the final exam. And so the TA actually will go through all the answers for this practice exam for the final. Okay, and because that we didn't finish all the lectures yet, so what we decided is that instead we make a live recitation on this Wednesday. We replace it with we will try to deliver this recitation by using a pre-recorded video. Okay, so basically the TA will record the video. He will also that he will upload all the necessary notes. Okay, on the Blackboard. And in the video, he will try to go through all the practice exam problems for the final. Okay, so again, okay, so on Wednesday no live recitation. Okay, and instead, okay, the TA decided that he will make that the recitation time on Wednesday to serve as his office hour. Okay, because he said that the TA's office hour he put on the Wednesday afternoon, it's not a good time for most students because that a lot of students complain that they it conflict with their schedule. So he decided that from this week he will move his office hour to the recitation time. Okay, he will also make an announcement on the Blackboard for all this kind of thing. Okay. Again, okay, this final practice exam for the final is only cover the contents for the chapter 7 to 10. Sorry, chapter 6 to 9, and I will also make our previous 2 practice exam for the midterm 1 and midterm 2. I will also make them available. Okay, so in another word, you can still review all those practice exam problems for the midterm 1, midterm 2 to help you to prepare for the exam, to cover the contents from the chapter 1 to chapter 5 of our textbook. Okay, so this is for the our plan for the exam. And do you guys have any question for the final exam? I see some people checking.
I have a question. So if we're gonna have the recitation not this week, we're gonna have it next week. Is there any way we can have a set of office hours so we can come with questions from that recitation video?
Yeah. So let me talk about it. Okay. So for the based on the school schedule, okay, we only have 1 recitation left. So it's this Wednesday. Next Wednesday, the semester, all the teaching sessions will be, it's done. Okay. So next Wednesday we do not have the recitation, but the TA will hold the office hour definitely next week. The office hour, both TA and me, we will have our office hour available. So if you have a question, you can go to our office hour to ask us any question. And regarding to this video, okay, recitation video, because I will only make this practice exam problems available today, so I think that it's better that you guys try it yourself before you watch the video. Okay, so the video will not be available on Wednesday. The video will be available sometimes around this Friday, so that you will see the solutions there. All right. Any other question? No question for the exam? All right. Yeah, and before I start this lecture, the last thing is for the homework, okay? We will have one last homework, okay, which will cover all the chapters from chapter 7 to chapter 8 and chapter 9. Okay, so I will assign it today. And definitely, okay, right now you won't be able to answer all the problems because that we only finished chapter 7. Okay, and we will also we will also finish the most part of the chapter 8 today. Okay, I will let you know that you know, when I assign the assignment, I will let you know that which part you should be already be able to finish it. Okay, which part you have to wait to the until next Monday. Okay, and you can begin to do it. Okay, and so that is everything. So let's start today's lecture. And on the last lecture, right, we finished to talking about dimensional analysis and similitude. So now we are moving to the last topic of the class, and we are going to focusing on the incompressible and viscous flow. I remember that in the chapter 6, right, when we're talking about we're focusing on the incompressible inviscid flow, right? That is where we developed the Bernoulli equation, right? And now we are making the flow viscous. And incompressible means that the density is constant. Yeah, in other words, it also means that the Mach number is small, because we know that the Mach number is also used to, to characterize the compressibility of the flow, right? So usually Mach number is smaller than 0.3. We consider the flow is incompressible. Okay, and so we have two chapters to cover this viscous flow. Chapter 8 is for the internal incompressible viscous flow. Internal means that the flow is inside of tubes or pipes or channels. Okay, and on the chapter 9 we will focusing on the external incompressible flow. Okay, external flow is like the flow over a flat plate and the flow over an air wing. Okay, those kind of things. Okay, and again, okay, we only cover like a part of this a part of contents in these chapters. Okay, we will not cover everything. We're focusing on the laminar flow. Okay, because we will not talking too much about the turbulent flow. Okay, and for the laminar internal flow and incompressible laminar internal flow. Okay, and so before we go to the equations, okay, we want to talk about that what the flow patterns looks like. Okay, what the flow field looks like if you have a viscous flow, flowing inside a pipe. Okay, and when the flow is viscous, okay, and we are based on what we introducing on the chapter 2. Okay, on the chapter 2, right, is very is in the very early of this semester. Actually, we distinguish the flow field into different categories, right? Viscous flow, inviscid flow, internal flow, external flow, laminar, turbulent flow, and so on, right? So when flow is viscous, right? So there are two possible flow regimes. One is called the laminar flow, and one is called the turbulent flow. And laminar flow basically means that the flow is very well organized. Okay, all the particles they're moving is like one smooth layer over another layer, right? So one layer here, another layer here. Okay, and so for this flow inside this pipe, so you can think that there are, their path line is like a straight line. Okay, and laminar flow happens when the viscous force is dominated. Okay, because that we know that when the flow is viscous, right, it's more organized, like your glue, right? It's like it's very organized, right? They're moving very slow, there are no chaotic things happening inside, right? And so, but when the viscous force is not that big, okay, in other words, if the initial force is big, it's much bigger than the viscous force. Okay, your flow field may become very chaotic. When I say it's chaotic, this means two things. The first thing is that, if you look at this flow structure for this turbulent flow, you see that they are streamline, they are not, well organized. Okay, there are small, vortices, created inside of the flow field. So this is the first thing. The flow pattern, okay, is not that well organized or not well organized. The second thing is that for the turbulent flow is that the quantities inside, like no matter is the density, the velocity, or the pressure, okay, they behave some statistical properties, behaviors. Like they have some random behaviors. If you try to do using your experimental equipment to measure the things inside, okay, the pressure field, the velocity field, at a different time you may measure different values. Okay, so because this is statistical behavior of all these flow properties, okay, it will also happen, which means that all these raw density, velocity, pressure, temperature, all these flow properties, they will fluctuate. They will fluctuate, okay, around their mean value. Okay, so that's why we see that the flow becomes a turbulent flow. Okay, and because that's the Reynolds number, right? In the last lecture, in the last chapter, we know that what the definition of the Reynolds number, right? Reynolds number is the initial force over the viscous force, right? And when Reynolds number is small, which means that because Reynolds number is let me write it down, okay? It's what? It's a rho of u of d over mu, right? So it will be the initial force over the viscous force. So when Reynolds number is small, which means that your initial force is much larger than your viscous force, right? You have laminar flow. Okay. When Reynolds number is very large, which means that your initial force is much larger than viscous force, then you will have turbulent flow. Okay. And in another word, okay, we use Reynolds number to determine that what flow regime will be. And usually we will have value. This RECR. This CR means critical. Okay, this is called the critical Reynolds number. Okay. So when your Reynolds number you calculated is smaller than this critical value, we see the flow is laminar. And when this Reynolds number is larger than this critical value, we see the flow is turbulent. Okay, and what this value should be, what this critical value should be, is determined from the experiments. Okay, from many experiments, people find that for the flow inside a pipe, okay, the critical Reynolds number should be around 2300. Okay, so you need to remember this. Okay, so in another word, if the Reynolds number you calculated for this flow, using this d is the diameter of the pipe, this u is the mean flow velocity. Okay, maybe I should use this v bar here. Okay, this v is the mean flow velocity of the fluid inside the pipe, and rho is the fluid density, and mu is the viscosity of the fluid. So if you calculate this Reynolds number, if it is smaller than 2300, you know that the flow is laminar flow. And if this Reynolds number is larger than 2300, you know that flow is turbulent flow. Okay, so this is the first topic we want to talk about, that for the flow pattern of the flow, for the internal flow inside the pipe. The second flow pattern we want to talking about is that we want to talking about the entrance effect. So what does the entrance effect means? So if you have if you assume that this is the inlet of your pipe, okay, and assume that if you have a uniform velocity, when I say the uniform, which means that this velocity is the same value on all this cross-sectional area, U0. Okay, so when this flow with this uniform velocity profile go inside this pipe, so what will happen, right? And we know that flow is viscous, right? And for the viscous flow, we usually have the no-slip boundary conditions. What the no-slip boundary condition means? It means that at the wall, right? At the wall, because the viscous effect, the velocity of the flow at the wall should be 0, right? So which means that this velocity profile will not maintain this uniform profiles. Okay, So like for example, if it's the flow field in the here, okay, so the velocity here has to be 0, and then it's moving to something like this, and in the middle here, so maybe as this region is still uniform, and then it will reduce to 0 again. Okay, so because this viscous force, right, viscous effect, with this friction effects between the wall and the fluid, okay, we will develop a layer, starting from this tip, inlet tip, close to the wall, this layer, and at the inside this layer, you will see that the velocity gradient on this radial direction, on this r direction, this radial direction, on this inside this layer, you will see that this velocity changes, like changing from the 0 at the wall to the velocity to somewhere. Okay, if this is if this viscous region is not affect the region here, okay, so the value here will be still equal to the U0. Okay, and this thin layer, okay, due to generated due to this wall friction, and we call this what? We call this boundary layer. So what the boundary layer means? The boundary means that inside this boundary layer, this is the region, the shear stress is significant. Okay, so only in this region you have the velocity gradient, and we know that mu, we know that tau equal to mu of du dy, right? Du dr, right? So only you have the velocity gradient, you have the tau, right? So which means that only in this region, because that only in this region you have this du dr is not equal to 0, then you have the large tau value. Okay, and outside this region, okay, outside the region, because there are still no velocity gradient, and then this region will be no tau value. Tau will be 0 in this region, and this region here, it's called inviscid curve. Inviscid curve. Okay. When I say this is inviscid, that means that the fluid is has no viscosity. No. Okay. It's the mu is still not 0 in this region. Okay, because it's the same flow, the same fluid, right? It's only because that the velocity gradient inside this region is 0, so that the tau equal to 0. Okay, and so that inside this region here, it looks like there is no viscous force, right? So that's the reason we call this inviscid curve. Okay, so this is what happens when this uniform flow profile just entrance this pipe. Okay, and with this flow going along this flow direction, along this x direction, and this is x direction, along this x direction, and this boundary layer, right? This thickness, right? They will keep increasing. The thickness of this boundary layer will keep increasing. Okay, which means that the region for this inviscid curve will keep reducing, and until to some point here, the boundary layer will generated from outside of the wall. They will meet at the center line. Okay, so which means that everywhere will become the viscous, the shear force everywhere for this viscous shear force become dominated. And in this region, then in this field, in this region, right, because there's no inviscid layer, right, so everywhere will be you will see that everywhere you will see the velocity gradient. Okay, you will see the velocity changes on this radial direction, all through all inside this pipe flows. Okay, and this region we will call is a fully developed flow. Okay, and in the previous region, before this boundary layer they meet, that because we know that we have the inviscid curve and the boundary layer region. This region we call is the entrance length. Okay, and we are going to talking about this more about this boundary layer in the next chapter when we're talking about that external viscous flow. Okay, especially for the flow over a flat plate. Okay, we will introducing this, to study this boundary layer more. Okay, but for the internal flow, okay, you can use this concept to understand that why this region is entrance region and why this is fully developed region. In the entrance region, because the boundary layer is their thickness is keep growing. Okay, so the velocity profile will keep changing. The velocity profile will keep changing. Okay, along the x direction. So the profile here looks like this way. The profile here maybe will looks like this way. Okay, and this profile will definitely be different with this one, and this profile will be different on the profile here. So on this x direction, you will see that this profile will keep changing. Okay, but after the flow become fully developed, and this velocity profile will not be changing anymore. So on this location, you see this velocity profile, and on some other location where downstream, you will see exactly the same profile there. This profile will be same on the fully developed region, and that is why that is another way we can determine that define that how we define the fully developed region. We can just assume that if the velocity is only a function of r, not only function x. This velocity u, right, is only changing on r direction, will not change on x direction. Okay. In other words, partial u, partial x equal to 0, or u is only a function of r, then we see the flow is fully developed. Okay. So this is the second topic we want to talking about for the flow pattern, for the flow, inside of a pipe, and how we determine this entrance length, right? So usually that we want to know that how long this entrance length will be. If this entrance length is very small, comparing to the full pipe length, right? So if this entrance length is much smaller comparing your full pipe length, then maybe you can neglect this entrance region effects, right? And on the other word, if this entrance length is very significant comparing to your full pipe length, then you won't able to neglect the entrance effects. Okay, so keep this in your mind. And how we determine the entrance length, again, okay, it's determined by experiments. Okay, we determine it experimentally. And for the laminar flow, when the Reynolds number is smaller than 2300, right? So this is how we determine for the laminar flow. The entrance length L divided by the pipe diameter D is approximately equal to 0.06 times the Reynolds number. Okay, so this is rho times V times D over mu is a Reynolds number. This is Reynolds number, right? This is definitely Reynolds. This V, we add a bar here. This which means that this is the mean. So V bar is the mean flow velocity, right? And how we calculate this mean flow velocity? You can calculate it from the mass flow rate or volume flow rate, right? So V bar can be equal to Q is the volume flow rate divided by cross-sectional area. Okay, and so we can know that if you have this U0, okay, at the inlet, so you can also calculate the mass volume flow rate here, and because that the flow is incompressible, so we know that the volume flow rate is the same all the x direction, right? Because we do not have any density change, so the volume flow rate will be also constant. And at the inlet, the volume flow rate can just be calculated as A times U0, right? So yeah, in other words, from this correlation, you will know that this V bar is just equal to U0. The mean, so no matter later on, okay, how your velocity profile changes, no matter how it changes, if you try to calculate the mean velocity, you will see that their mean velocity will be just equal to this U0 value. Okay, you see that if you want to use this profile to calculate the to do the integration, okay, you can also calculate this V of bar equal to 1 over A, okay, divided by over A over this U over dA. You can also do that, okay, but you will see that the value will seem as this U0 if you use the profile here. And so this gives us that you know what's how we know that what's the entrance length. So you know you can determine that whether or not this entrance effect is significant or not. Okay, and in this class we will focusing on the fully developed flow. Okay, so this is what we are going to focusing on, because that for the fully developed flow with this assumption here, U is only function of R. The profile will not keep changing on the X direction. It's possible for us to develop the analytical solutions from the Navier-Stokes equation, right? Again, okay, for the viscous flow, right? Because flow is viscous, so our governing equation is what? It's not the Euler equation. It's not the Bernoulli equation. It's the full Navier-Stokes equation we are going to solve. Okay, so keep this in your mind. And any questions so far, guys? No question? Okay, so for the internal viscous flow, right? We are focusing on two cases. Okay, two fundamental benchmark problems. The first one is that the flow between two infinite parallel plates. Okay, so this is the first problem, benchmark problem we are going to study. So we will, you know, we will try to solve that, you know, our you know governing equations for this problem. Okay, and then we can try to find that for the fully developed flow, laminar flow. Okay, focusing on, we also focus on the laminar. Okay, so it's fully developed and laminar. So we have two important words here. First thing is that we study only the fully developed region. Second thing, we're only focusing on the laminar flow. Okay, we are not interested right now in the for the entrance region and for the turbulent flow. No, okay, we're only focusing on these two. Okay, we want to see that for this problem, okay, after we solve the flow equations, what the velocity will look like, profile will look like, what the viscous stress force, the friction force will look like. Okay, so this is the first benchmark problem we want to study. The second problem is for the fully developed laminar flow inside a circular pipe. Okay, this is for the between the two parallel plates, right? So this is the just two plates. Okay, and the second problem, then we will change this to a circular pipe to see that what the flow looks like. Okay, so let's start in for the first one. And for this flow between infinite parallel plates, we consider two cases. The first case is that both plates are stationary. Okay, so which means that on the top plate and the bottom plate, they are both stationary. Okay, and they are, and also we know that the distance, okay, so these two plates are separated by a distance of a. Okay, so the distance between the two plates is a. Okay, and when you see that the infinite parallel plates, which means that if we define this is x direction, this is y direction. Okay, so sorry, this is x direction, this is y direction. Infinite plate means that on x direction, this plate is infinite long on x direction, and also we assume the flow is one-dimensional flow. Okay, flow is only on this x direction. So in another word, on the z direction, what is z direction? Z direction is the direction perpendicular to your screen. Okay, on the z direction, we also seeing that you know this plate has infinite length on the z direction. Okay, so plate has is infinite, also infinite on the z direction, and also that the flow has no v and w velocity on the you know for this flow. The flow is only has u velocity, and because it's fully developed, right? So we know that u is only a function of y. U is not a function for x. Why? Because that is fully developed. For the fully developed flow, the velocity profile is not changing on x direction. So u is only a function of y, not a function of x anymore. And v and w equal to 0. We do not have any velocity on the y direction and the z direction. Okay, and for this flow, right, if we want, because that there is no, both plate is stationary, right? So if we want the flow to move, we have to apply a pressure gradient, okay? So the flow can only be moved in this situation, in this scenario, by if you have a pressure, if we assume this is P1, if we assume this is P2, P1 has to be larger than P2 so that to make the flow moving to the right. And if the P1 is smaller than P2, then the flow is moving to the left, right? So the driving force for this flow motion is a given pressure gradient. Okay, so keep this in our mind. And how we solve this problem, right? We know that the governing equation is the full Navier-Stokes equation, right? And for this problem, definitely we can simplify the Navier-Stokes equation a lot. Okay, how we simplify it? First, we know that it's one-dimensional flow, right? So V and W equal to 0. So that is the y direction and z direction momentum equation is gone, right? We do not have the y direction and z direction momentum equation. And also that we know that the velocity u is only a function of y, not a function of x, because that is fully developed, not changing on the x direction velocity profile. So you can using this to simplify, greatly simplify both the mass conservation equation and the momentum equation in the Navier-Stokes equation. And also that if you want to solve that equation, right, you need to have some boundary condition to solve it. The boundary condition is that so this BC means is the abbreviation for the boundary condition. Okay, so the boundary condition is that at y equal to 0. How we define the y? We define the y here, right? So y equal to 0 is this point. It is on the bottom plate. Is no slip condition, so u equal to 0. And the y equal to a on the top plate is no slip condition, so u equal to 0 again. Okay, so with all this, you can greatly simplify your Navier-Stokes equation, and with this boundary condition, you should be able to solve the solution. You should be able to solve that what this profile will be, u and this u. You can find this function u as a function of y. You can find that. Okay, and our textbook didn't using this method. So our textbook, okay, using an alternative method to solve this problem. That method is, again, okay, to starting from a differential control volume inside the flow field. Try to starting from to apply the x direction momentum equation on that control volume to see that if we can find the solution directly. Okay, so remember, so I just want to say that we have two methods to solve the problem. Okay, the first method is that you're starting from the Navier-Stokes equation with this simplification, and with this boundary condition, you can solve that equation directly to find that what the function u y will be. And the second way is what the textbook method, so which we will go through by details. Okay, in this method, we define a small control volume inside this flow field. Okay, assume this is control volume, and assume that we know at this center of this control volume, assume that we know that what the pressure P will be and what this tau yx will be. Right, tau x is the x direction stress on these y faces, right? And then, because we want to apply the x direction momentum equation, right? So we want to see that what the x direction force is working on this control volume. Okay, so on the left face, and we know that the x direction force will be the pressure force. Okay, and because we know the pressure at this center point, right? So you're using Taylor series, you can know that the pressure at this left face will be equal to this one. This is from the Taylor series. And then using this pressure times this area of this surface, right? dy times dz, you get the force. And similarly for the right surface, okay? And you can get the pressure using the Taylor series, will be this value. This will be the pressure on the right face. Okay, and then again times the area dy times dz, you get the what the pressure force on the right face. And again, okay, remember that the pressure force is always toward the inside of this flow, this control volume. Okay, so this is normal stress force, and also you will on the top surface, top face and the bottom face, you will also have the shear stress force on the x direction. Remember, we're only focusing on the x direction force, okay? And on the top one, okay, again, using Taylor series, so this will be tau yx value on the top face. And then you times the, this is the stress, right? You times the area dx dz on the top face. Okay, this will give you what's the shear stress force on the top face. And similarly, you will also have what is the shear stress force on the bottom. And remember that these two forces, they are not the same direction. They are all, try to strike and try to deform this this control volume, this fluid particle counterclockwise. It's counterclockwise, clockwise. Clockwise, I make a mistake here. Okay, it's tau x. Yeah. Okay, and so we have all these forces here. Okay, and let's take a look at the x momentum equation for this control volume, right? So this is the surface force, and this is the body force, right? Let's assume that the body force is neglected, so we neglect the effects of the gravity. Okay, and this is a transient term for the momentum, right? Inside this control volume, and because the flow is a steady flow, so we assume this is 0. And what is the last one? Last one is that what is the momentum flux enter into the net momentum flow, the net momentum flux enter into this control volume, right? And the last one, it will also be 0. Why? Because that we know that the flow is fully developed. So when we have fully developed flow, you know that the velocity profile on the left and on the right is same. Why? Because that is fully developed. This u as a function of y, right? Because u is only a function of y, right? It's not a function of x. Okay, so the u profile on the here and the u profile here will be exactly the same. And because that the flow is also incompressible, so which means that the momentum flow moving in on the left hand side will be equal to the momentum flowing out on the right, because that the velocity profile is same, right? And also that this area is same. So in this way, okay, the last term is also 0. So this is due to the fully developed. So this is the x momentum equation, right? So if you cancel all these 0 terms, you remove all these 0 terms, the only thing you left is what? Is this fsx equal to 0. In other words, the resultant surface force on x direction equal to 0. So which means that if you add all these 4 terms, they should be 0. So this is what our x. So after we apply this x momentum equation inside this control volume, this is what we find. Okay, so remember that y this is 0, right? So this is we neglect the gravity force. This is because the flow is steady, and this one is because that flow is fully developed. Okay, how much flowing in will be just equal to how much flowing out. So this has to also be equal to 0. So the only thing left is this one. Okay, and now with this result in our mind, and and from these pictures you see that on the left face, right? So this is the pressure force. So on the left face, this is the pressure force. On the right face, this is the pressure force. On the bottom face, this is what the shear force on the positive x direction. And on the top face, this is what the shear stress force on the positive x direction. You add all this x direction force on this 4 surface together, add them together, they should be equal to 0, right? So you should have this dFL plus this dFr plus this dFb plus this dFt. It should be equal to 0. And something, this p and p will be cancelled when you add them together. The tau x will be cancelled. Okay, and then you add for all the terms, you have this dx times dy dz, dx times dy dz, dx times dy dz, right? So you can cancel this dx dy dz on both sides. So what thing you left? So this is the only thing left. It's showing you that the pressure gradient will be just equal to, on the x direction, will be just equal to the tau yx gradient on the y direction. Okay, so this is the result we get. And so what is tau yx will be? From the Newton's viscosity law, we know that tau yx will be mu times du dy, right? And so if you substitute this one into here, into this tau y d tau yx dy, okay, and also remember that u is only a function, and also remember that u is only a function of y, right? So if you substitute to this one, so this one will be giving what? This one will change it to mu d square u of dy square, right? D tau yx over dy will change it to this one. And because u is only a function of y, so all this term, all this result on the right hand side, this one is only a function of y, right? You see that? And then if you take a look at the left hand side, so this is partial p, partial x. Okay, so this telling us that it's only this p partial p is this term is only a function of x. Okay, so for this equation, right? So for this equation, you see that the left hand side is only a function x, and the right hand side is only a function y. So the only way they can be equal is what? Is that they are all equal to a constant, because there are no other way they can be equal, because this is only a function of y and this is only a function of x. So the only way they can be equal is they are all equal to the same constant value. Okay. So in other words, they're telling us what? They're telling us that the pressure drop for the fully developed flow inside a pipe is a constant. Okay, so which means that on this fully developed flow, for this fully developed flow, the pressure drop actually is linear. It's dropped like this. If you draw a p of a function x, so this curve will be a straight line. The pressure will dropping at a constant slope. Okay. Okay, so we found that by applying the x direction momentum equation, okay, by applying the x momentum equation, we found that d tau y dx over dy equal to dp dx has to be equal to constant. Okay, and then we can just try to, knowing this is constant, we can try to solve this tau yx by just integrating on this constant on y, right? So you try to solve this one as a constant, just solve this differential equation, integrate this equation on the both sides for y. You find that tau yx will be dp partial p partial x, because this is constant, times y plus c1. Right, so this is constant, right? And then because because this tau yx equal to mu du dy, right? So you replace this tau yx with this mu du dy here, and then you integrate on, because u is only a function y, right? You integrate this differential equation on y again on the both sides. You can find out what the u value will be. Okay, so it's showing us that our velocity profile will be given by this one, and this c1 and c2 are two unknown constants due to this integration, because we do this integration twice, right? So we have two unknown constants, and this unknown constant c1 c2 can be determined from the boundary condition, right? So what's the boundary condition? At y equal to 0 is wall, right? So velocity is 0. You substitute y equal to 0 into here and make u equal to 0. You can find that c2 has to equal to 0. And the second boundary condition, at y equal to a, the top wall, it should be 0. Velocity also should be 0. You substitute into it, make y equal to a here, make u equal to 0. You can find that the second unknown constant c1 will be equal to this value. So you put this c1, c2 value back to this u value here, you will finally get that what is the fully developed velocity left profile for the laminar flow inside a circular pipe, inside between the two stationary parallel plates. So this will be resolved. U will be just equal to a squared divided by 2 mu dp partial p partial x. So remember, this is a constant. Again, this is a constant. Okay, times this y over a squared minus y over a. So this is the u. This is what the velocity. This velocity profile looks like. It's given by this equation. And we can see that from this part, we can see that this equation is a parabolic equation. Okay, and after you know this velocity profile, right? Again, right? Because there is this tau yx equal to mu times du dy, right? You can substitute this u to this du dy times mu here. You can find what this tau yx will be. Okay, so you can find that the shear stress distribution. Okay, this tau x equal to mu of du dy. You substitute this u into here. You can find that this tau x will be equal to this value, a times partial p partial x, and y over a minus y over 2. Okay, so this is the result we find here. Okay, so we can see that using this method, right? We do not solve the Navier-Stokes equation directly, but by just simply apply this x direction momentum equation on this small control volume, right? We can also find that what the u as a function of y. We can also find what for this fully developed flow what the velocity profile will look like. Okay, after you know the velocity profile, you can calculate the shear stress distribution tau yx because equal to mu of du dy. And after you have this profile, you can also calculate what the overall volume flow rate will be, right? The volume flow rate will be just equal to velocity times dA, right? And let's assume that because we know this A is the cross-sectional area, right? So for this problem, if we want to know the cross-sectional area, let's assume that on this z direction, on this direction perpendicular to the screen, this plate has a width of small l. Okay, let's assume that we have small depth l in the z direction. Let's assume that so that this dA can be equal to l times this distance, right? Times this dy here, right? dA will be l times dy, and then you integrate this y from 0 to a. You substitute your u value inside. You substitute this u you got here, profile here, into this one. You try to calculate q. Okay, and the result will show you that this q over l. Okay, because this l is constant, you can divide it on the both sides. You see that the q over l will be just equal to minus 1 over 20 or minus 1 over 12 mu partial p partial x times a to the cubic. Okay, so this is telling us that the volume flow rate per unit depth in the z direction equal to this value. And you have this negative sign here, right? And why this negative sign? Because that partial p partial x is smaller than 0, right? Because that we know that only your pressure is dropping, right? The pressure on the left is pressure larger than pressure on the right. Then flow will move into the right, right? So this partial p partial x is smaller than 0, so that flow can move into the right. That's why you have minus sign. Okay, so that so the overall value here will be a positive value for the volume flow rate, because we know that the volume flow rate is always a positive value, right? And because that partial p partial x is constant, okay, and if we know the p2 p1 p2 value, okay, if we know that the 2 pumps, right? If we assume that for the whole pipe, for the flow, the whole flow inside this pipe is fully developed. Let's assume that the P1 is on the left and the P2 is on the right. Let's assume that this pipe has a length of L. Okay, so we can write that this your partial p partial x, because it's a constant, it can be just equal to P2 minus P1 divided by L. Okay, and also because that P1 is larger than P2, right? Because that's the reason the flow can move, and we can write this as minus delta P, right? Because delta P is the P1 minus P2 is larger than 0. Okay, you substitute this one into here. You can see that okay, This QL again can be rewritten as this A cubic over 12 mu delta POL. So this is another result we get from this full developed flow analysis. Okay, and we can also calculate, after we calculate the volume flow rate, right? We can also calculate the average flow velocity, right? Average flow velocity is what? It's just your volume flow rate divided by your cross-sectional area. Okay, so you just need to using this value divided by the A, right? And you will get this result here. What is A? Remember, A is what? A is A equal to L times A. Okay, cross-sectional area is the depth L times this distance A, right? So you're using this Q value you get here divided by this value. Okay, and you'll find that this will be your mean average velocity will be. This gives you mean average velocity. So remember, this is the value of velocity you are used to define the Reynolds number. Okay, remember that we need Reynolds number to determine that whether or not flow is laminar or turbulent, right? This V bar is this average velocity is the velocity we use to define the Reynolds number. So this is the average velocity, will be equal to this again. Okay, and remember, parallel x is constant, so everything is constant. Okay, and you can also find that where you have the maximum velocity, because that you see that the velocity is a profile is keep changing on this y direction, right? You want to see that at each y value, this profile has a maximum value. And again, okay, from this one, you see that it should be y equal to a over 2 at the center line, right? So to do that, you simply need to for this you do if you want to find the extreme value, right? You make the first derivative of the function equal to 0. So you just do du dy equal to 0 to find that at which y it has a maximum velocity, right? So this is you substitute u result into here. So this is what the du dy will be, and if this is equal to 0, we find that y will be a over 2. So which means that again, y is a over 2 is this center line, right? So we see that the maximum velocity happens at the center line, y equal to a over 2, and you substitute y equal to a over 2 into this velocity profile. You find that what the u max will be, the maximum value, the maximum velocity will be just equal to this one. This result is you get by substitute this y equal to a over 2 into this velocity function. Okay, and after you find that, you can comparing this u max with your v average. You'll find that actually your maximum velocity will be 1.5 times of your average velocity, right? Because if you compare this one and this one, so this is 1 over 8, this is 1 over 12, right? You see that this is 3 over 2 times this value. So in another word, so for this, if you look at this picture, so if this is u0, and we know that this will be u average, right? This is u0, right, at the inlet, and we know that the v average will just equal to u0, right? And then for the fully developed flow, this length here, this is where the flow, this is fully flow, right? This is the length where the flow has the maximum velocity, right? So this length should be 3 over 2 length of this length, because this is V bar, okay? And this is the maximum U max for fully developed flow. So you find that U max you will be 0 to V bar, okay? And so this is all the result we get, okay? Remember that all this shear stress distribution, the volume flow rate, the average velocity, the maximum velocity, all this is we just simply derived from this velocity distribution we obtain, okay? And remember that the result here, right? In this result, right? In this velocity profile, we define y equal to 0 at the bottom plate, right? This is how we define the y. But sometimes, okay, people like to define this y not from the bottom plate, but from the center line. Let's assume that we define this y prime at the center line. Instead, we define the y at the bottom plate. The orange point on the bottom plate, this orange point on the y and on the center line. Okay, so it's possible that you can do a transformation of the coordinate so that you define a new y prime, so that y prime will be y minus a over 2, so that y prime equal to 0 is the center line. Okay, so by this way you define y prime as this center line here, and x we do not change it. Okay, so if you substitute y prime equal to y minus a over 2 here, okay, so in another word, y prime equal to y minus a over 2, right? So in another word, you get that y equal to y prime plus a over 2, right? You substitute this one, y equal to this one, into this result here, right? You replace this y. You replace this y with y prime plus a over 2. You replace this y as y prime over this y also as y prime a plus 2. So you can change this. You can obtain the u velocity profile under this xy prime coordinate, right? So by doing that, you can find the new profile of u as a function y prime will be in this form. Okay, and if you plot this one on this picture here, okay, and you make this y direction as y prime over a, and you make x direction with u divided by u max, the maximum value when y prime. So in this case, you have the y prime equal to 0 will give you u equal to u max, right, at the center line. Before is y equal to a over 2 give you the maximum velocity, right? But now because that we move the coordinate to the center line, so this y prime equal to 0 will give you the u max. Okay, you can find substitute this y prime equal to 0. You can again to replace, you get this u max, the same u max here. Okay, and if you do this plot, okay, make this x coordinate as this non-dimensionalized velocity, you will see that this again you will see this a parabolic profile for this velocity distribution. You will see that the velocity has a maximum value at the center line. Okay, so this is all the result we obtained from this velocity profile we obtained. And remember that this velocity profile is only valid for infinite flow, fully developed laminar flow between infinite parallel plates when both plates are stationary. Okay, so this is only valid for this one plus this one, both plates are stationary. Okay, and from here we can develop many useful flow features. Okay, and we have an example problem to showing you that how to utilize these results we got. Okay, and please read this one so we can go through it together. Okay, so for this problem, you will see that from the picture here, you will see that why this is a flow between two plates, right? It's like a flow inside an annulus, right? Cylindrical annulus, rather than flow inside the two plates. The reason is that for this problem, right, the flow is flowing in this small annulus, right? But the gaps of this annulus gaps, okay, is very small comparing with this cylinder diameter. Okay, so in that cases, okay, if you go to see the local if you try to zoom a local region of this flow field, it's approximately looks like a flow between two street plates. Okay, so that's why is that we still can using our previous solutions we developed for the flow between two stationary fully developed laminar infinite long plates to use it here. Okay, and this is only validated between this if this gap here is much smaller than this diameter d. Okay, and the problem asks us to calculate the the leakage flow rate, right, the volume flow rate. So we can using this our volume flow rate result here, this value here, to calculate it, right? So this is the value here, and the plate width will be L, okay, and so what is L will be, right? L is the L will be equal to pi of d. Okay, because for this problem they are leaking on all this L direction. They are leaking all this on this L direction. Okay, so L will be equal to pi d. So you substitute into this equation, can calculate Q will be equal to this one. Okay, and the pressure drop is also given here. Pressure drop is given by 1.0 ampere, okay, and megapar, and you just substitute into it, and from the our appendix you can find the fluid properties for this engine oil. Okay, you substitute the things inside. Okay, for everything, all these quantities here, you can quickly find what the Q value will be, what the volume flow rate will be. So this is the leaking rate for this engine oil. Okay, and after you finish this one, right? Again, okay, we need to verify that whether or not this is valid, because we do not know that the flow is laminar or turbulent. So again, you can from this volume flow rate, you can calculate with this V average, right? And you can calculate the mean velocity, and using this mean velocity, you can calculate what the Reynolds number. Okay, so in these cases, we find that the Reynolds number is very small, very small, 0.0375. So this is much smaller than 2300, right? So it's so this will be 2300. Okay, so we know that the flow is laminar, which means that the equation we use here is valid. Okay, so this is one first simple example problem to showing you that how to utilize this fully developed laminar equations for the flow between two stationary parallel plates. Okay, so this is the first case. We also have the second case. So what is second case? Second case is that let's assume that only the bottom plate is stationary, but the top plate is moving with a constant speed u. Okay, so if you look in the flow field, the velocity profile in this fully developed flow will looks like it will be zero velocity at the bottom, but on the top, the flow velocity will have the same velocity with this u because it's no slip condition, right? There is no slippery between the fluid and the wall. So the fluid velocity at the top, you will also have the same velocity, this u here. And then your profile looks like this way. Okay, how we solve this problem? How we solve this? So we can starting from the same analysis on this x direction momentum equation on this control volume. So everywhere, everything will be the same procedure as this case. Okay, we can still repeat this process, and everything will be same. The only difference is that the boundary condition is changing. Now at y to a, u will be not equal to 0, will be big U here, and everything here will be same, and everything here will be same, and until we obtain until we go to here, until we obtain this velocity profile, all the procedures will be same as the previous case if the both plate is stationary. Okay, we will still get it. We will still obtain this velocity profile with these two unknown coefficients C1, C2. Everything will be same as before, but the only difference is that the boundary condition now will change. at the bottom is same as before, at y equal to 0, u equal to 0, but at the top, at y equal to a, now u is not equal to 0 anymore, u will be equal to b du. Okay, so because the boundary condition is changed, right? So if you substitute these two boundary conditions into this u functions, you can find this C1, C2 value, right? So you find two new C1, C2 values. C1 will be this one. In this case, C1 will be equal to this value, and C2 will be equal to this value. These two C1, C2 will be different with the C1, C2 value we obtained from the previous case. Okay, you substitute this C1, C2 value into here, you can find that what's a fully developed velocity profile. For this case is if the upper plate moving with a constant velocity u. Okay, you substitute it, you get this one. So this one, again, okay, this one is not is different with this one we obtain here because the boundary condition changed. The C1, C2 value is also changed. Okay, so we can just repeat the same procedure we get before. Okay, now we have this new velocity profile, right? So we can again we can calculate what the tau y x will be. Again, tau y x will be mu times du dy. You substitute this u into it. You can calculate the new shear stress distribution for this case will be equal to this function. Okay, you can also calculate what the new volume of flow rate will be. Just do the integration as before, right? Because q of L should be integrated from the 0 to a, okay, u of dy, right? You can calculate this one. And after you calculate the q, you can calculate what the average velocity will be, right? Average velocity will be q over a, will be equal to this one, right? And you can also try to find where is the, you have the maximum velocity, and you just do du dy equal to 0. You can find that, okay, for this case is your maximum velocity actually is not in the center line. And because there is a part of x equal to is a negative value, right? We know that the pressure gradient is negative value. So actually you will see that this value will be some point above the center line. So your maximum velocity will happen somewhere above your center line, right? Because this quantity is larger than 0, right? Because this is smaller than 0, so you get a negative line. This is larger than 0. Okay, and so this is the, so if your part of x is smaller than 0, okay, this is your velocity profile looks like. Okay, your maximum point will be above the center line, and your part of x equal to 0. Okay, because in these cases, okay, you do not need because in these cases you do not need a pressure gradient to drive the flow to move, because that is you have a movement on for the upper plate. Okay, it's different for the previous case. The previous case, for the both plate is stationary, you need a pressure gradient to push the flow to move. But for this case, you really do not need the pressure gradient. Why? Because that the top plate already is moving, and with this no slip condition, the top plate will try to drag the flow field to move. Okay, and if it is a pressure drop, in this case, if your pressure gradient is equal to 0, then your velocity profile will be a straight line, right? If your pressure gradient is equal to 0, all this term is 0. Only this term is left. You know that your velocity field is a straight line. And if your pressure gradient is smaller than 0, you will have this kind of similar. You will have this kind of flow field profile. Okay, so this is the cases is that the only difference between this case 2 and case 1 is that the only difference is that we change the boundary condition on the top. That's the only thing. The governing equation is still same as before. The physics inside is still inside, is same as before. Only the boundary is different. Before, on the top plate is stationary, and this one, the top plate is moving with a constant velocity u. And because this boundary condition changes, everything is changing. The velocity profile is changed, and consequently, all this shear stress distribution, this volume flow rate, average velocity, and point maximum velocity is also changing. Okay, so just keep this in mind, okay? So you need to, for these two cases, right? I suggest that you, because it's very hard to remember this equation, right? So I suggest you guys, okay, in your cheat sheet, okay, you should write down all these equations in your cheat sheet, so that when you see an exam problem, you know that for which cases which equation you use. Okay. Any questions so far, guys? No question. Okay, so we also have an example problem for this problem. Okay, so this is similar than our previous example problem. The only difference is that the inner cylinder now is not stationary. The inner cylinder actually is rotate with an angular velocity 3600 round per minute. This is angular velocity. Okay, and also that for this one we assume that there is no pressure gradient. Okay, so they're bearing no load. Okay, so dp dx equal to 0. So this is the case is dp dx equal to 0. So the velocity profile will be straight line. Okay, so this dp dx is 0 everywhere. Okay, so this is the cases. So the question is asking that what is the torque required to turn the journal and the power to dissipate it. Okay, and so how you calculate the power, right? You need to calculate the torque, and the torque is coming from the viscous force, right? We want to know that what is torque, this torque value, what's the viscous force generated on this on this inner cylinder surface here, and what's this torque value times the area will give you the viscous force, right? And what this force will generate torque, to this orange point, and this torque times this omega angular velocity will give us the power required. Okay, so for this problem is pretty it's also very straightforward. So this is the case 2 condition where one plate is moving, and the velocity will be just equal to this big U will be just equal to this omega times this R, and R will be d over 2, right? So will be omega d over 2. So this is what the big U will be. Okay, and this distance clearance A is given. Okay, and to calculate the stretch force, we need to know tau x, right? So we're using this tau x equation. But for this case, it's dp dx equal to 0. So the only thing left is mu u over a, right? So the only thing left is mu u over a. Okay, so we need to calculate the u, and the u, as I told you, u is equal to omega times r, right? So omega d over 2. Okay, and omega is 36 round per minute, right? You need to change this to the radian per second. Okay, and you substitute this omega inside it. You can calculate what the tau value. You calculate what's the viscous stress on this inner surface, on this surface of this rotating cylinder. After calculate tau x, you can calculate what's the force. This force will be this tau x times the area. Area is the pi d over L. Pi d is the pi over d is this parameter of this cylinder, and L is the length of this cylinder. So pi d, this pi d over L will give you the area. Area times this tau x will give you the friction force F. And if you want to calculate the torque, you just simply need to calculate time multiplied by radius, right? Because that all the viscous this viscous friction force, right, is in the normal direction of the R direction. So just times the R, you can calculate the torque. After you calculate the torque, you want to calculate the power, you just need to use the torque times the omega. Right? From our dynamics class, if you take your dynamics class, you know that the power is calculated from the torque. For this rotating system, the power is calculated from the torque times the omega. Right? So you can calculate what the overall power required will be this, right? Okay. And so we finish this example problem. And again, okay, you can also try to verify that whether or not the flow is laminar or not, right? Because so that you can try to calculate again. You can try to calculate what's the average velocity u, okay, You can try to calculate average velocity, and you substitute the things here. You find that okay, Reynolds number is only 43.6. It's also very small, very small value, so you know that flow is a laminar. So that means that this equation is, this equation we use here is valid. Okay. And so this is one example problem. We have one more example problem for the textbook. And so this example problem try to, using the same momentum, different momentum, analyze the control volume for our problem, try to see to develop the velocity profile. Okay. So for this one, I will not go through it, and please, you need to read it yourself. Okay. When you got time. And here I finish today's class, and the next class we will continue the second case for this fully developed laminar flow. The first case, remember, is that of the flow between the parallel plates, right? And in the next class, we will focus on the second case, which is the flow inside a circular pipe. So what the velocity will be for the fully developed flow, and then how we calculate the pressure drop, how we calculate those viscous stress distribution. Okay. And any question, guys? So if there are no question, I will just finish today's lecture. Any question, guys? No? Okay, so before I finish, just remember your two things again, okay? Because some students maybe come late. On Wednesday's recitation, the live recitation on the Wednesday is replaced by a recorded video from the TA, okay? Because that recitation, he will go through a practice exam problem for the final, okay? And second thing is that I will also assign a new homework later tonight, okay? The homework will cover like chapter 7, 8, and 9. This is our last homework. And I will also let you know that which part of homework problem you should already be able to do it now, and which part of problem you need to wait until next Monday to finish it. Okay? Any question, guys?
When will the homework be due?
I will give you plenty time, okay? And but I won't make it very close to the final exam. So at least 2 weeks, okay? At least 2 weeks. So, but like maybe 1 week after. I do not have a calendar on my hand. So it will be 2 weeks from today, okay?
Okay.
No problem. Any more questions? No? Okay, so if there is no question, I will just finish today's lecture. And remember that if you have any question for your second midterm exam, feel free to, and also any question for the final, you can feel free to go to my office hour on Wednesday. All right? Okay, bye everyone.
Have a good day, Professor.
Bye.